In this lecture, we'll be looking at the tool of the squeeze theorem for limit computations of sequences. So recall, an infinite sequence of real numbers is an ordered list, A1, A2, A3, and 4, so on and so forth. We call AN the nth term, and these are the ways we denote, typically, sequences. We have an important result that says if your sequence is tethered to a function, then they have, if the function has a limit as x goes to infinity, so does the sequence. So if our function looks like this, and our sequence is tethered to it, then our sequence has to have the same limit as the function as x goes to infinity. And again, think of the function as the road. If the road is getting towards L as x goes to infinity, so do footsteps on it. The squeeze theorem is a very handy theorem for computation of limits of sequences. So suppose we have three sequences. AN, think of that as our given sequence, LN, and UN. And we're using those names so that LN, you want to think lower, and UN, let's think upper. So we have this relationship starting at some value capital N for the index. The nth term in the lower sequence is less than or equal to our given sequence, which is less than or equal to the nth term in the upper sequence. And that's always true from there on, from capital N on. If the limit as n goes to infinity of the lower sequence equals L, and that also is the limit as n goes to infinity of the upper sequence, then the given sequence AN has to have the same limit L as n goes to infinity. And the way we can think of this is here's n, and suppose our lower sequence is looking like this, and let's set our limit. So this is our limit L. So our lower sequence has this limit of L as n goes to infinity, but our upper sequence also has that same limit. This means that our given sequence, our A sub n, this set of inequalities tells us that it's in between. But if you see the result graphically, there's not much wiggle room as you get further down. This sequence is forced to have the same limit, L, because it's being squeezed between the upper and the lower sequences. So this is a very handy theorem for some limit computations, and a classic example is one like this, where you have either a sine or a cosine in a numerator and a denominator that's getting large. And so when we look at this, the intuition is that in the top, cosine of n, that oscillates, or maybe we should say stays between, or stays in the interval -1 to 1. We know no matter what you feed cosine, it's something between -1 and 1, inclusive of the endpoints. The n squared, that's going to infinity. So you have a ratio where the top is bouncing around in the interval -1, 1, and the bottom is exploding. So this should go to 0. But how do we actually show this? And the key is the squeeze theorem, and we do it as follows. Start off saying, okay, we know that cosine of n is inside of -1 to 1, no matter what n is. And now let's see if we can do some algebra on these inequalities to build our expression. Well, we know 1 over n squared is positive for n non-zero. So we can multiply every term here by 1 over n squared and retain the inequality. So we would get minus 1 over n squared is less than or equal to cosine of n over n squared, less than or equal to 1 over n squared. And we now note that we have our sequence squeezed between two simpler sequences. So we can now argue, well, we can take limits of all three of these functions here and retain the inequalities. So the limit as n goes to infinity of negative 1 over n squared is less than or equal to the limit as n goes to infinity of cosine of n over n squared, less than or equal to the limit as n goes to infinity of 1 over n squared. And we know that each of these sequences on the right and on the left are going to 0, which tells us 0 is less than or equal to the limit as n goes to infinity of cosine of n over n squared, which is less than or equal to 0. And the only way a number can be both greater than or equal to 0 and less than or equal to 0 is if it is, in fact, 0. So we've just proved that this sequence has a limit of 0. And again, it's important to recognize that up here we thought about it and kind of told the story and felt it out. We developed intuition for it, which was different than mathematically showing that the limit is 0. So when you do these types of problems, it's often good to try and do both. Try and get some intuition for what's happening and feel things out. That can give you an idea of what your answer should be, and then work out the details to get there.